Curvilinear coordinate systems 3. A circular disk centered at the origin of a coordinate system is rotating at a constant angular velocity omega 0 in the counterclockwise sense. Part A. In Cartesian coordinates, what is the velocity vector of the point P located at the Cartesian coordinates 1, 1? And in B, in polar coordinates, what's the velocity vector of point B located at the Cartesian coordinates 1, 1? Okay, so we have a point B, which is part of the circle here, located at point 1, 1. So there are corresponding polar coordinates r and phi. There will be a unit vector er hat on the radial axis and e phi hat on the polar axis. And the velocity, tangential velocity, is given by v is equal to its magnitude v in e phi hat direction. And this is also related to the angular speed of the rotation. It's omega 0 times the radial distance r to the center in e phi hat direction. This is for a uniform circular motion. So that's what we know. Now the radial distance to the center r is square root of x coordinate and y coordinate squares of the point B. So it's square root of x squared plus y squared. So this is square root of 1 plus 1, which is square root of 2. And therefore, we can write the velocity vector v as omega 0 r, but r is square root of 2. So it is square root of 2 omega 0 in e phi hat direction. Now let's move on to part A of the problem. The relationship between Cartesian coordinates and polar coordinates is given by x is equal to r cosine phi. So we take the projection of this position vector onto the x-axis. This is our x-axis, this is our y-axis. And the y component of the position vector is r sine phi. Which means we can write the position vector of this point in using Cartesian coordinates x ex hat plus y ey hat, which is equal to r cosine phi ex hat plus r sine phi ey hat. And now the unit vectors er hat and e phi hat we can find. We take a derivative of the position vector with respect to r. This gives us, you can see here, the derivative will give us cosine phi and sine phi for this term. So we will have cosine phi ex hat plus sine phi ey hat, and the magnitude of this vector hr, which is our scale factor, is magnitude of del r, del position vector del r. This is square root of sine square plus cosine square. So sine square phi plus cosine square phi square root, which is equal to 1. So the first scale factor is equal to 1, and therefore we can write our unit vector on the radial axis er hat is equal to cosine phi ex hat plus sine phi EY hat. And for this point, 1, point P, we have tangent phi is equal to 1. So we have this right triangle here, 1 divided by 1, so tangent phi is equal to 1, which means we're talking about the angle phi of 45 degrees. All right, and cosine 45 and sine 45 are equal. They're equal to square root 2 over 2 or 1 over square root 2. So we can write this as 1 over square root 2 EX hat plus 1 over square root 2 EY hat. So that's our unit vector. On the other hand, we can look at the phi derivative of the position vector, del r del phi, to find the unit vector in the tangential on the tangential axis. The derivative with respect to phi is minus r sine phi. Here it's plus r cosine phi. So minus r sine phi in EX hat direction plus r cosine phi in EY hat direction. And the corresponding scale factor we can calculate. Let's move this a little bit to this side. The scale factor h phi, now you can see, will be the magnitude of del r del phi. In this case, I will obtain r square root cosine square plus sine square for the magnitude here. So this was simply equal to r. So I can write E phi hat, the unit vector in the tangential direction, E phi hat is equal to, so I have to divide this by r minus sine phi EX hat and plus cosine phi EY hat and minus sine phi is minus 1 over square root 2 when phi is equal to 45 degrees, minus 1 over square root 2 EX hat, and we have plus 1 over square root 2 EY hat. And this gives us our velocity vector V is equal to omega 0 times square root of 2 E phi hat, and E phi hat is minus 1 over square root 2 EX hat plus 1 over square root 2 EY hat. All right, and therefore we can write our velocity vector V is equal to, now you can see that I'm going to have a cancellation of square root 2's here for these two terms, and I will obtain minus omega 0 EX hat plus omega 0 EY hat, or I can write this as my velocity vector of point P is equal to omega 0 EY hat minus EX hat. So this answers part A of the problem. In Cartesian coordinates, what's the velocity vector? This is the velocity vector written in Cartesian coordinates. Part B was asking in polar coordinates, what is the velocity vector? Well, that we have actually already done here at the beginning. So we talked about the r, the transformation between polar coordinates and Cartesian coordinates. R is square root of x squared plus y squared, which is square root 2. So it's omega 0 r in E phi hat direction. So we can just write the answer here in polar coordinates. The velocity vector is square root 2 omega 0 in E phi hat direction. Okay, so in this problem we have worked in polar coordinates. We were talking about the uniform circular motion. The tangential velocity is the speed. It has the same speed everywhere in E phi hat direction. So this is rotating in the counterclockwise sense. And we are looking at point 11. That's point P. And we're trying to write the velocity vector for this point. And we have the relationship between the angular speed and the tangential speed is v is equal to omega 0 times r. R is the radial distance to the center of the rotating disk, and this is in E phi hat direction. So we have these unit vectors ER hat and E phi hat, which are perpendicular to each other. And therefore, we can write this velocity vector as square root 2 omega 0 E phi hat, which is the answer to part B in polar coordinates. In Cartesian coordinates, I have to know how to write the unit vector E phi hat in Cartesian system. For that, I have to take a derivative of the position vector, which is r cosine phi ex hat plus r sine phi ey hat with respect to phi. That's what we did here, minus r sine phi ex hat plus r cosine phi ey hat. The scale factor, which is the magnitude of this vector, is r. So dividing it by the scale factor, we obtain the unit vector E phi hat. So you can check the magnitude is square root of sine square plus cosine square, which is 1. And the phi for this point P is 45 degrees because tangent phi has to be 1. So it is minus 1 over square root 2 ex hat minus sine 45 plus cosine 45 ey hat. So that's my E phi hat. So square root 2 omega 0 times E phi hat. The square root 2's will cancel and I will have minus omega 0 ex hat plus omega 0 ey hat or omega 0 ey hat minus ex hat as my answer.